All right, linear regression or linear models, or what we'll call simple linear regression or SLR in this book. This might be the most important subject in the whole book and maybe the most important concept in all of statistics. It's going to be broken up over two sections. Here in part B of the video vignettes, we're going to talk about linear models and inference, in particular for the slope parameter. And in part C, in the next video, we'll talk about prediction for simple linear regression. So the linear model, emphasis on model because it's a specification for how data is generated probabilistically. We're going to think about the pairs xi and yi. So yi is going to be the random component, and it's going to be predicted through a linear equation given xi's. And those yi's are going to be observed with noise or errors. So those noise variables are going to have a Gaussian distribution. So this is how the probabilities are involved. So y is a linear function. We have an intercept and a slope. In middle school algebra, those might be a and b, or they could be m for the slope is kind of common. Lots of different ways to write that down, but in statistics, we like Greek letters for the unknown quantities. And so our Greek letters are going to be beta 0, or I'll sometimes say beta naught for the intercept, and beta 1 for the slope. So those are unknown quantities. The errors are also unknown quantities, so they're Greek as well, but they have a distribution. So we're assuming that those errors are on average 0 and have a spread around 0 that follows a Gaussian distribution with a variance of sigma squared. Sometimes you'll see this written a little bit more compactly, where the linear equation is inside the mean of the Gaussian distribution. So it's a little bit like this is a mu I to make a connection to chapter 2 or chapter 3 from the book. So each y has a Gaussian distribution with a mean of mu and a variance of sigma squared, but that mean of mu is a function of an x variable, an xi, so it's a mu I. And of course, we have n of these pairs of data values. So these are equivalent representations of the same model that's linear and still probabilistic and Gaussian. This is a more prescriptive relationship for y and x following a linear equation, so more prescriptive than correlation from part A of this chapter. And I'm going to show you how those two things are related a little bit later, so hold that thought. For right now, what I want to talk about is how to dial in estimates of the unknown quantities, which are this intercept and slope. And the answer is to maximize the likelihood. We have a Gaussian distribution involved, and so we can look at the joint density of all of the observations given the unknown parameters. Another unknown, I guess, there's a third one here, so I should write beta naught, beta 1, and sigma squared. Right? And for all of those parameters, I can use the likelihood and calculus to find estimates. So let me show you what I mean. So each one of these observations has a Gaussian density. So the Gaussian density looks like this. Right? So that's a PDF of a Gaussian distribution for each yi given parameter mu I. And I said mu I is a linear equation. So actually, if I correct all this to write in my my beta naught minus beta 1 xi squared. Then I've got this, that's ugly, this mu I appearing here to make a connection to the mu I there. And I have n of these, so they are IID, right? Independent and identically distributed errors. So I equals 1 to n for each data observation. And that is my joint PDF given the parameters. I didn't leave myself enough space. Right? That's the joint distribution. I always like to simplify that, if I can, to the part of it that involves things that don't have anything to do with the data and those things that do, and then bring the product into the exponent. So distribute the product through, and it becomes a sum inside the exponent. Whoops, I'm skipping stuff and making all sorts of mistakes. This is going to be kind of a long lecture, so I got to make sure I do everything just right. So minus 1 over 2 sigma squared. Then the sum I'm going off the screen here. You got to call me on that. Okay, so there we go. And then we take the logarithm of that, right? So the log likelihood is the same thing as the joint density, but viewed as a function of the unknown quantities instead of as a function of the data values. And then I take the log of 2 pi to the minus n over 2, but that doesn't have any parameters in it, so it's really just constant with respect to beta naught, beta 1, and sigma squared. Here I take the logarithm and I get a minus n over 2 log sigma squared. Sigma squared is a parameter that I'm interested in keeping track of. And then the logarithm, it's a natural logarithm, so it gets rid of the exponent. And I end up with just that. And you can see that a really important quantity in this analysis, we're going to take derivatives and set them equal to 0 and solve in a minute, but a really important part of this is what's called the least squares criteria, because I'm looking at the discrepancy between my model parameters through this mean and the data values squared. So sometimes people call this part of the criteria, the part that doesn't involve the sigma squared, as the ordinary least squares, or OLS criteria. So there's a connection between what I'm showing you involving a linear model and likelihoods and maximizing the likelihoods to something you may have heard of before called ordinary least squares. All right, to solve ordinary least squares or to maximize the likelihood involves calculus. You would do more or less the same thing. So let's get a little more space here. So I want to find the MLE. So what I'm going to do is I'm going to take the derivative of the log likelihood with respect to each parameter in turn. I'm going to start with the intercept beta 0 and set that equal to 0 and solve. So the derivative of the log likelihood with respect to beta, the only part that involves beta is the part that that is in this least squares, not the sigma squared part. So I'm going to be taking the derivative of this 1 over 2 sigma squared. It's actually negative, but this constant doesn't matter with because we're setting it equal to 0. Of the sum from I equals 1 to n of yi minus beta naught minus beta 1 xi squared. Okay, so when I I really don't need, oops, I'm not going to delete it. I'm just going to cross it out. I don't need that because I can multiply both sides of this equation by the reciprocal of that quantity and it goes away. And when I take the derivative, I'm going to get a 2 that I'm going to be able to play the same game with. And then by the chain rule, I'm going to get a -1. And I'll be able to cancel those as well by multiplying by -1/2 on both sides to get them to go away. So what I need to solve here by distributing through the sum, I'm going to have a sum of yi's, and I'm going to have n copies of beta naught, because there's no I in that. So when I distribute the sum through, I get n of them. And then I get minus beta 1 sum of the xi's. And then I can move beta naught onto the left side and then divide by n on both sides. And I'm going to get 1 over n sum of yi minus beta 1 over n sum of xi. And then I can rewrite that as y bar minus beta 1 x bar. So this is my estimate of the, I like to make those nice boxes. So let's do that. Okay, so there's my nice MLE for the intercept. My interpretation of this, I call this the means on the line estimate in the book, because if you pick a slope beta 1, I'm going to show you how to estimate beta 1 by MLE in a second, but given that value of the slope, you want your intercept and your average y value and your average x value to be a point on that line. And this is what builds the intercept so that the average y and x value is a point on the line. Remember, you can specify a line with a point and a slope. And here I'm specifying the intercept with a point, and I'm going to show you where the slope comes from in just a moment. Okay. So again, same game here. I'm going to set the derivative of the log likelihood with respect to another parameter. Now I'm going to do the slope equal to 0. And again, that's just going to involve the derivative of the least squares part. And I know what to put in for beta naught, because I just solved for it. So I'm going to get 2 copies of beta 1 in there. I got to be a little bit careful. I'm not going to embarrass myself by doing this live. It's in the book, so I'm just going to put ... C book. And I'm going to just jump to what the answer is. The answer has a really tidy expression. It's the covariance, or the estimate of the covariance, between x and y divided by the variance of x, or the estimated variance of x, which can be rewritten as the correlation between y and x times the standard deviation, or estimated standard deviation. These are all estimated quantities. So I really like this expression. Again, the details of how to get there on this are provided in the book, but I like this because it makes a nice connection between slope and correlation. So slope is correlation times rise over run. Remember rise over run from middle school? So I'm measuring rise statistically through the spread of y values, or the estimated standard deviation of y, divided by the spread of x values, or the estimated standard deviation of x. So slope is correlation times rise over run. And now we know the connection between linear regression, connecting SLR to correlation. Okay. Finally, I know we've done a lot of math, and one of the reasons I'm skipping the beta 1 hat estimate is because it's just way too much for this video, and I got to keep this video as short as possible. Fortunately, if we do the last parameter by taking the derivative of the log likelihood with respect to sigma squared, we've actually done this already. This is exactly as in chapter 3 with mu replaced by mu I, which is beta naught hat plus beta 1 hat, given the values dialed in above, times xi. And in fact, this value, if I also put a hat on it, sometimes people also write this as a yi hat, has a special name. It's called the fitted value. The fitted value is related to the actual data value. So the answer to this question is really what you would get in chapter 3, which I'm going to write out exactly the way it is in chapter 3. In chapter 3, we did the residual sum of squares to the estimated mu value. But in this case, the estimated mu value is different for each I because it follows the linear equation with the estimated slope and intercept parameters. And this difference between the data value and the fitted value has another special name called residual. There is more about fitted values and residuals in the book and how those work together in the analysis of simple linear regression that I'm going to skip here just so we can keep the video short and focused on the most important details. And there's some good homework problems that relate those residuals to the estimated coefficients as well. Just like in chapter 3, it's more common to use a different estimate that's not the MLE, that we're going to call S squared, that corrects for bias. And since there are two estimated parameters, the denominator is n minus 2 instead of n minus 1 in chapter 3 where there's only one parameter, mu. Now I've got two parameters, beta naught and beta 1, that I'm going to use in my residual sum of squares, and I'm going to write it out with the estimates now instead of with mu I, but you can make the connection squared. Okay, so this is what most people will use. All right? So those are all of the estimates of the parameters. And now I'm going to go to R and show you what that looks like on our frat dash data. So first of all, I guess I didn't anticipate here. I got to make sure I'm caught up with all of the code from earlier in the chapter because I'm going to use the same data. So I'll just go back up to the top here and grab the plot for the frat dash data, and let me reveal that plot for you. So now you should be able to see it. And then I'm going to go through the MLE for the simple linear regression model. So the slope is correlation, I've already called that R before, times the square root of Sx2 divided by Sy2. So correlation times rise over run. So the slope is about 1. That kind of makes sense in this example. There's an almost one-to-one relationship between time before a beer and time after a beer. And then the intercept is the y bar. I've already calculated y bar minus b1 times x bar. Whoops, y bar. So that's the intercept. I really like to use, I use B0 and B1 for beta 1 hat beta 0 hat and beta 1 hat. And I talk a little bit more about that in the book. It's just shorter than writing the Greek word out and then hat. So I like to use that instead. And now I can put that on the plot. We've used the AB line command for vertical lines in the past, but it's actually designed to take parameters A and B, A for the intercept and B for the slope. So I can do slope and then intercept, and then it'll put the estimated line on the plot. Okay, so that should be right. So that is the line of best fit. That is the ordinary least squares or MLE line. Okay. Now what else? We also have the estimate of s squared. So first for that, I need to calculate the residuals. So y hat, we can call that mu hat or y hat. In the book I call it y hat. So that's my estimated slope plus estimated intercept plus estimated slope times x. So really this is just putting in the estimated parameters in the linear equation. And then I can estimate S2 as the sum of residuals versus data values squared, and then divided by n minus 2. Okay, so there's my estimated variance. Okay, so that's estimation, and the next subject is uncertainty. So how do we test hypotheses with these estimated parameters? Okay, so let's go back to the whiteboard. I want to test hypotheses about the estimated parameters. So there are 3 parameters, so I could test hypotheses about each one. But the most important one, and the one that I'm going to focus on here, is the slope. Testing whether the slope is 0 or not is really important, because if the slope is 0, then x doesn't matter for y, because I'm going to take all those x's and multiply them by 0, and those y's are going to have a distribution based only on the errors. So this tells you something about the usefulness of the relationship between x and y. How useful is x for explaining y? But if you want to, you can test any other value of beta 1. It would be fine here. For example, it could be interesting to test beta 1 equals 1, which would tell us whether or not there's a 1-to-1 relationship between the times of these fraternity boys running before and after a beer. But I'm going to stick with 0, and in the book you'll see some other examples involving other values, and you'll have homework problems to test your understanding of that. And you'll see in the simulation where you can plug in any value of beta 1 that you want and see how that works. A really important ingredient, again, comes from chapter 3. We need to be able to use that estimated variances really have a chi-squared distribution. Everything ports from before, except we're going to replace n minus 1 with n minus 2. So this is a relationship that has been gone over and multiple times in chapter 3 that we're going to use in our simulation. So let me go over to R and show you what I mean by that. So I'm going to do a simulation. We already have a value of n defined earlier from the correlation examples. So I'm going to test for beta 1 equals 0, and I'm going to do a for loop, and I'm going to generate sigma squared values following that formula. Okay, so that's just following the formula. And then I'm going to generate y values from a Gaussian distribution with, I have n of them, right? And they're going to follow b0 plus b1 times x in the mean. And they're going to take square root of sigma squared in the variance. So that's just me following the linear equation. And then my estimate of the slope, we can call that B1S, is correlation between these y's and x's times rise. So that's the square root of the I could just write standard deviation of the y's, that'd be a good shorthand, divided by standard deviation of the x's. Okay. And I need to make some space to save all these beta 1 values, or these beta 1 hats. Okay, so now I have the usual setup. This is very similar to chapter 3, but I've got a 2 here where I would have had a 1 in chapter 3, and I've got a different mean, a mean that follows the linear equation. Oh, I've made a mistake here. I've got to use the null hypothesis. I need to use the beta 1 value that I want in my test, because the null hypothesis assumes that beta 1 takes on a particular value, and that particular value is 0. But you can plug in whatever you want if you want to do a different test. Okay, so now I think I can run that. And then I can do the usual visual of the null distribution. So that's a histogram of these virtual beta 1 hat values, and I need to show you that plot. So there is the histogram, and then I can look at value estimated from the data. So AB line V equals B1. Okay, so to me it looks like this estimated value from the data is an extreme value under the null distribution. So I think I'm going to reject the null hypothesis, but I can be more precise with a p-value. So I can do 2 times mean of B1S greater than B1 for a two-tailed p-value. All right. I've got this sinking suspicion that I've made a mistake somewhere, but I'm not seeing where it is, but I think this is more or less right. I guess that's what you get for doing it all live. We'll be able to check our work in just a moment with some of the mathematics. Okay. All right, let's go back over to the whiteboard. The math way is more work. Just going to take but doable. Okay, so let me remind you that beta 1 hat is syx over sx squared. We wrote that down above, and just to write that all out, I've got a sum of xi minus x bar, yi minus y bar, divided by sum over I of xi minus x bar squared. So that's just me writing out sxy and sx squared. The 1 over n minus 1 that would appear in the numerator and denominator cancel. And a nice little homework exercise here is that the numerator will simplify. I encourage you to work this out. a little bit. So all I've really worked on is the numerator. It gets a little bit of a simplification because of how x and y are related together. This is not a particular linear regression thing. This is just about summing up these products. And the reason for writing it that way is I get to like draw a loop around these things and define a variable called wi. So what I really have is that beta 1 hat is a weighted average of the y values, where the weights are these interesting ratios. The reason for writing it like that is I can calculate the mean of this estimate with respect to the distribution of y. So here I'm really thinking about these y's now as random variables, as capital letters. I can use linearity of means to distribute the expectation through, and then I can break out what this means. Each one of these is a beta 0 plus beta 1 xi, right? So I've really got beta 0 times the sum of the weights plus beta 1 times the sum of the weighted xi's plus the error term, the sum of the weights of the expected values of the errors, which are all 0. You can also show that this term evaluates to 0. There's a little identity in the book that helps you work that out. And then all of these go to 1. So I encourage you to either figure that out on your own or look at the help for the identities that are provided in the book. So I get 0 plus beta 1 plus 0. So to wrap it up, this is beta 1. So the expected value of the MLE for the slope is the actual unknown slope. So that means that it's unbiased. Okay, so now I know the mean of the distribution of the MLE. And in fact, we already know a result from chapter 4, the asymptotic distribution of the MLE. We know that the MLE asymptotically has a mean that's unbiased, but in this case, it's not an asymptotic result, it's an exact result, and we have derived it. We can play a similar game with the variance. So the variance of the estimate of the slope is, by linearity of variances, the square of those weights times the variance of the individual yi values. And we know that these are all sigma squared. So I'm going to get sigma squared times the sum of the weights squared, which, again, there's a identity provided in the book, but it's not too difficult to work out what the result is. So the variance of the estimate of the intercept follows this formula. And again, we know that from the asymptotic distribution of the MLE from chapter 4 that the variance can be worked out asymptotically, but here this is not an asymptotic result. It is an exact result, and it has a similar interpretation as the asymptotic result because of the n in the denominator. This tells me that with more data, I get a smaller variance. So I get a tighter estimate around the true value, which is beta 1. And another thing that affects inference is the spread of the x's. So if the x's are more spread out, I can get a more accurate estimator of the slope. There's kind of a leverage interpretation going on here. This helps you design the experiment. So if you can choose what x's to use in order to observe y's, you can get a lower variance estimate of your slope. Okay, so just sort of summing up what we know, we have that the estimated slope has a mean of beta 1 and a variance of sigma squared over n minus 1 times sx squared. And we know that sums of Gaussians are Gaussian, so we can write those two facts together as a Gaussian distribution. Summarizing the whole null distribution in closed form. If we replace sigma squared with an estimated value, yeah, that's correct, we can use a t-test. Right, so what I mean by that is a t-statistic for the slope, that's why I'm writing t1, is the estimate for the slope from the MLE minus whatever value you want to test about. We're going to use 0 divided by a standard error. The form of the test is estimate minus want to know divided by standard error, where the standard error is the same as the formula for the variance above, but with sigma squared replaced by s squared. And this t-statistic will have a t-distribution with n minus 2 degrees of freedom. So we can use that to do a t-test. So if I go back over to R, the math way via t-test, I have SB1 is s squared, or the square, we better take the square root because it's a standard error is always square rooted from the variance, divided by n minus 1 times sx squared. Okay. Oops, I must have a parentheses problem. I didn't close the square root, so we'll do that again. And then my t-statistic is b1 minus beta 1, which is 0, divided by that standard error. And then I can do 2 times pt minus abs of t1 and minus 2 degrees of freedom. Okay, so I must have not made a mistake earlier because I'm getting more or less the same answer with this mathematical calculation as I got earlier with the simulation. The setup is very similar for testing about the intercept, but it's not as common to do that. So I'll leave that to you in the book and on the homework. And similarly, it's not as common to test about the variance, but you can do that using chi-squared distributions. What I really want to move on to next is prediction, and that's going to be in part C of this chapter's video vignettes. So that's it for now.